Hello. Today let's discuss how you might use your home computer to simulate a mission from Earth to Mars. It's commonly assumed that to do this simulation you must first use an Earth-centered coordinate system. And when the spacecraft is sufficiently far away from Earth, switch to a Sun-centered coordinate system. Then, when your spacecraft is close to Mars, you must switch to a Mars-centered coordinate system. This requires two coordinate system transformations. But is this necessary? Vector equations are available for you to use which locate the planets in our solar system relative to our Sun as a function of date and time. And if we accurately know the position of Earth and Mars relative to the Sun, then we also accurately know the position of Mars relative to Earth. To find the position vector from Earth to Mars, simply subtract the two known vectors, b and a, as I show in the image you now see. I don't know how accurate these published vectors are, but let's assume that we can locate a planet with a standard deviation error equal to 1 kilometer relative to the Sun. Therefore, we can locate Mars relative to Earth with standard deviation error equal to 1,400 meters. This assumes that the errors average to 0 for repeated measurements. I show this calculation in the image I now show. The question you should now ask is, does my computer have a variable with enough significant figures to allow me to store the distance between Earth and Mars with sufficient accuracy? Most standard software codes now have double precision numbers with at least 15 significant figures. So, if Mars is on the opposite side of the Sun relative to Earth, the distance between the two planets is about 378 billion meters. Therefore, it requires only 12 significant figures to state the distance to an accuracy of 1 meter. Your double precision variable with 15 significant figures can state the distance to an accuracy of 1 millimeter. I doubt that we know the distance to that accuracy, but if we did, your computer could easily store it and use it in calculations. In summary, if you accurately know the position of Mars relative to Earth, you don't need to accomplish coordinate transformations to simulate a mission to Mars. You can simply use the Earth-centered coordinate system for the entire mission. But what about gravity from Earth's Moon, Sun, and other planets? Shouldn't they all be included in the spacecraft equation of motion? Yes, they should, and since you know the position of each of these bodies as a function of date and time, you can easily include their gravitational forces in your equation of motion. Recall that the Newtonian equation of motion is given by the equation that I now show. In this equation, r with arrow over it is the vector distance between Earth center and the spacecraft, and r with the arrow and double dot over it is the spacecraft's vector acceleration relative to the center of Earth. However, when including the gravity vector from another body, we must find the gravity vector at the spacecraft due to the other body and then subtract from it the gravity vector at the center of Earth due to that body. This is required because all forces applied to the spacecraft must be relative to the center of our coordinate system, and that is the center of Earth. To make this more intuitive, remember that Earth is also being accelerated by the other bodies. Therefore, the center of our coordinate system is accelerating, and its acceleration must be subtracted from the spacecraft's acceleration before we can calculate the motion of the spacecraft relative to our coordinate system. So, let me summarize. If you accurately know the position of all the heavenly bodies versus date and time, it's not necessary to perform coordinate transformations inside our solar system when modeling a mission from one planet to another. This simplifies the mathematics and allows you to use a single equation of motion for the entire mission. Some might say that the calculations are more efficient and faster if you switch to a Sun-centered coordinate system because you can assume that the Sun is large enough that it is not accelerated by other planets and moons. This eliminates the need to subtract their effects on the coordinate system's origin. However, the Sun is being significantly accelerated by other bodies in our solar system, and this causes the Sun to wobble. Is this wobble small enough to be neglected? Our satellite orbit simulator does not currently support mission design outside the near-Earth area. However, it could easily be modified to do this. We simply need to include the gravity contributions for all major planets in our solar system. We will consider doing this in the future. Thank you for watching this video. If you find it useful or informative, please give it a like and recommend this channel to others. Also, leave comments if you have recommendations for changes to this video or ideas for new videos. Goodbye.